Agricultural drought assessment using standardized precipitation evapotranspiration index in Google Earth Engine. Hello everyone. Today we are going to walk through a Google Earth Engine script designed to assess agricultural drought. Drought isn't just about a lack of rain, it's about the balance between the water falling from the sky and the water evaporating from the ground. To quantify this, we are using the SPEI, the Standardized Precipitation Evapotranspiration Index. Unlike the standard SPI, which only looks at rain, SPEI accounts for temperature and evapotranspiration, making it excellent for agricultural drought monitoring in a warming climate. In the next few minutes, I will explain every single line of this code, transforming raw satellite data into actionable charts that classify drought severity over a 24-year period. Step 1. Setup and Visualization. We assume you have already defined a geometry variable named ROI, region of interest. Line 1, Map. Center object ROI tells the map canvas to fly to your specific region and adjust the zoom level automatically so the whole area fits on the screen. Line 2, Map.addLayer adds the visual boundary of your study area to the map. We leave the visualization parameters empty for now, which just gives us a default gray or black polygon, labeled study area. Step 2. Loading the dataset. Now, we access the data archive. Line 6, we call EE. Image collection to load the dataset provided by the Spanish National Research Council. This is a global grid dataset. Line 7, select SPEI 12 month. This is crucial. SPEI comes in different timescales 1, 3, 6, 12 months. We are selecting 12 months, which represents long-term hydrological drought. Line 8, filter date. We are restricting our analysis to the period from the year 2000 through the end of 2024. Step 3, calculating the mean. The SPEI dataset is a grid of pixels. To make a chart, we need a single number representing our entire study area for every month. Line 13, we use .map function image. This creates a loop that runs over every single image in our 24-year collection simultaneously on Google servers. Lines 14 to 18, image.reduce region. This is the spatial reduction. Reducer, we use EE, reducer.mean to average all pixels inside our boundary. Scale, we set this to 55,055 kilometers. This is important because the native resolution of the SPEI dataset is roughly 0.5 degrees, or 55 kilometers. If you set this too small, like 30 meters, you slow down the computation for no reason. Line 18, .values.getZero simply extracts the raw number from the calculation dictionary. Lines 20 to 23, finally, we return the image, but we use .set, SPE_mean, mean value, to attach the calculated average as a new property, metadata, to the image. This prepares the data for the next step. Step 4. The classification logic. Raw numbers are great, but words are better for communication. Here, we classify the values based on the standard McKee classification system. Line 30, we retrieve the SPE_mean we calculated in the previous step. Line 32, we start a large nested if statement. YEE algorithms.if. Because this code runs on the server, we cannot use standard JavaScript if/else statements. We must use Earth Engine's server-side conditional logic. The logic. Feature null. We are creating a feature, a database row, that has no geometry null, but contains a dictionary of data. We convert the system time to a readable date string. We carry over the mean SPEI value. We carry over the text classification label. Step 6, charting the time series. Now for the visuals. ui.Chart.feature.byFeature, this creates a standard trend line. We feed it to our droughtFC table. We define the x-axis as date and y-axis as mean_spa. .setChartType, LineChart. This connects the dots to show the trend. We set the title and label axes. This chart gives us the continuous trajectory of water availability. Step 7, the categorical scatter plot. This second chart is more sophisticated. ui.Chart.feature.groups, this function groups the data based on a specific category. seriesProperty, drought_class. This tells the chart to use different colors based on the text label we created earlier like normal or extreme drought. setChartType ScatterChart. We don't use lines here, we want distinct dots. The colors. These hex codes are specifically chosen. Blue represents wet periods, gray is normal, and critically orange and red represent the severe and extreme drought periods. Conclusion. Show the resulting console with the charts generated. Finally, we print the charts and the raw table to the console. When you run this, you won't just see a line moving up and down, you will see a color-coded history of agricultural stress in your region, allowing you to instantly pinpoint years where crop failure was likely due to climate factors. And that is how you build an automated drought monitoring system in 8 minutes. Thanks for watching.